We have more than 30 students today.
Way. All right. Okay. Let's get started then. Shall we? We already wasted like 7 minutes. So I want to continue today just talking about this local planning, and then it brings up a bunch of issues that we have to still deal with. So this is the topic still. It's what the algorithm was, if you recall this one-liner, and so we're gonna just talk about this single line. You take the maximum over all the actions where you take a random Bellman operator over the action value functions. You apply it to a 0, capital H times, and you have this initial state S naught. And you calculate these action values recursively for all the actions, and then choose the action which gives you the maximum action value. And the question is this a good idea? What does it buy us? So what does it buy us? Anyone wants to answer that question? What does this buy us? Why are we doing this?
Can save us some upfront computation.
Can you be more specific?
I guess we don't have to compute the right action in every state in advance.
Yeah, right. So we are localizing computation to S naught, the initial state. What do we expect to see if we do this? What's the goal? Anyone?
Avoid the dependency on the state set size. Yeah.
Oh yeah, but like, okay, I can avoid that. That's very easy. Let's just AB A1, the first action. That avoids it. It's very cheap too. Just return that. So yeah, like the goal has two aspects. Little compute and that's not enough. Small compute is never enough. That's always easy to satisfy. We also want
Correctness.
which means epsilon optimal. I see that Vlad was typing epsilon optimal. So maybe the algorithm should have some input. Well, I like to call it that, but and then we want what? Data optimality of what? Well, what does it mean? That what is data optimal here? What is going to be data optimal?
The value function.
Of what?
That state.
But like states have values, or yeah, there is the optimal value, but like we're not doing that.
Oh, the action value.
But okay. So action value like Q star, or
I guess Q pi.
Pi. Okay, so there is some pi here. Well, what is that pi?
Policy.
Yeah, what policy?
Oh, I guess induced by the whatever agent it could be about taking argmax of a value function.
Or argmax of this?
Yeah.
Yeah. So if the agent is doing all this computation, and when it's doing this computation, I guess for every S naught, it's going to choose a new operator, which is a random approximation to the, well, new stuff. So given an S naught, it chooses this random approximation to the Bellman optimality operator, does this calculation, returns an action. And so this is your planner. So this does this computation. Something comes in, we call it S naught. Something comes out of the planner, we call it A. And it goes into this outer loop. And the planner is using the simulator model to come up with T hat, which has a copy of the word, which is an MDP. And then the action is sent to the word. And the word is sending us states. And the planner used in this closed loop way induces a policy pi. Right? This is the policy such that the probability that this A at S naught equals A when the state is S naught. Right? So every state we can run the planner. That means generating this random guy. And well, this calculation all depends on, S naught. So there is a certain probability that this action takes a certain value, and those are the action probabilities. And then we continue running this policy. And so the delta optimality is going to mean that this policy has a good value function. It has a value function that's close to the optimal value function up to an error of delta, which is the input to the algorithm. And somehow we want calculations to be efficient. And here we're going to go as far as saying that, well, the complexities of planning per state compute cost is bounded by something like a to the power a over delta something. Well, we will compute. And there will be some 1 over 1 minus gamma, and then I don't know. I can't remember quite the formula, but we'll calculate it hopefully today. So this is the setting. Is this clear? All right.
There's a question in the chat.
Yeah, okay.
So Vlad asks that we haven't shown anything that allows the policy to be deterministic. So, is this related to the fundamental theorem? And does the planner's policy have to be stochastic?
So if we want to achieve complexity that is independent of the size of the state space, then we argued the last time that we better resort to a randomizing simulation model. So this is like a generative model of the, or simulator. So generative model of the MDP. And the reason for that was because otherwise we would need to calculate things like what's the predicted value given a future value function, something, at a given state, given an action. And this in a product could take as much time as the number of states. And if you have too many states, then if you only have like a very simple tabular representation for these transition vectors, then no algorithm, you can prove no deterministic algorithm. I mean, like no algorithm, like if the input is given in the form of these vectors, then no algorithm can avoid searching through this vector, because you can hide some needle in this haystack, so to say, thing. So imagine that the dynamics is deterministic, but you don't know what the next state is. And you can try different actions for different actions. One of the actions is going to get you to heaven, but you don't know which. Well, if the input is given as this long vector of probabilities, then you better search through this vector. Otherwise, you won't see whether this action is actually going to get you to the goal. So this was on homework 0, right? So if you wouldn't need to do this calculation because you don't have any other access to the MDP, you don't have this randomizing access to the MDP, you only have this tabular access to the MDP, then you will need to do this much calculation. And this is what we want to get away from. So in a way, the answer is just, yeah, like if you insist on deterministic everything, then you sort of have to insist on some representation like this. And if the representation of the MDP is ill-chosen, right, this vector-based representation, for example, then that is already disaster. You can have other representations, and I added to the lecture notes things like you sum up the probabilities, and then you could reduce the computation from linear in S to logarithmic in S. Maybe that's a homework. But yeah, even that is not independent of the number of states. And it is only this change in how we think about that the MDP is represented that allows us to get away with computation cost that is independent of the number of states, which is quite interesting. And it should make us think whether this change in the representation of the MDP is real or not. But I would say that it's quite real, right? Because if you have a deterministic system, you can directly calculate what the next state is. So that's like a simulator. And like this tabular representation with vectors, it's just such an inconvenient and unnatural representation. Now, of course, like if you have a deterministic system, then this also means that there are other ways. Actually, if you have a deterministic system, then there is nothing random about this algorithm, right? Because this operator is going to be deterministic too, right? then you get away with a deterministic algorithm. So we're just inheriting here the randomness of the simulator. We are not inducing extra randomness into the algorithm. And so unlike in homework 0, where we were trying to see the factor of 2 in the needle in haystack problem by using a randomized algorithm, here we are not using randomization in the same way. It just happens that without this generative model viewpoint, insisting on like a vector-based representation of the MDP, you wouldn't be able to come up with algorithms, like no one would be able to do that, that can run in time that's independent of the size of the state space. So you have to do this change, and then this kind of forces you into this corner. I hope this is clear. It's quite a nice discussion point, actually. Anything else? Okay. All right, so how far did we get? So the last time, so first definitions, right? Let's be quite specific. So you have these states and actions, and to each state action pair, we want to, for each of them, we want to generate a bunch of next states. So I'm going to denote this by S prime 1, SA up to S prime M, SA. And these are generated from the underlying transition kernel of the MDP by calling the generative model. So this is where you call the generative model, call simulator. But at the moment, let's just imagine that we do this for every state action pair. So this list, this is a list. I call it CSA. And I will also want to have the list that just collects all these lists into a big list. Right. So that's like the next state generated from a given state. So once you have this, you can define this t-hat operator, which is going to be of the type that works on action value functions and returns action value functions, and it mimics what the Bamon optimality operator would do on such functions. In particular, if you apply it to a function q, which takes 2 arguments, this q function takes 2 arguments, then what this calculation does, it returns a function such that the function awaited at the state action pair SA is equal to the immediate reward for this pair plus gamma times the average over the m next states in this list. So this is CSA because these are the children of this state action pair. And just so one step back and look ahead. So I need to take the action value at S prime and A prime and take the max in A prime. So that sort of mimics what the Bamon optimality operator would do, which was the same, except that, so you can call this MQ at S prime, hiding the max in this operator M. And if you do this, then there is a short way of writing the Bamon optimality operator with this M operator applied to Q, and then that gives you a function over the states, and then you can average these according to the next state distribution given the state action pair as A, and then you just add this to discount it and add it to the image reward. That's the Bamon optimality operator for action values. And we also introduced these sets. I mean, okay, so once you have these sets CSA, so you can view this as inducing a directed graph over the state space, where the edges would be just so the edge set would be that you have S, and S prime is an edge. It's a directed edge. If S prime is in CS, it's a child of this state. Okay, so here I'm kind of taking the union, like mixing a little bit up the notation, but I hope that you follow. I don't want to introduce new notation for all of these. Like sets, list, you can say it's an element of a list, right? Like it's fine. So these are the edges. You can imagine that you start. So you have this SA pairs. These are the states themselves, and for each action at those states, there are a bunch of next states, and then these induce these random edges. That an edge means that there is an action such that with that action, one of the states, these states in this list was the state where the arrow is going. Right? So you just get this big random graph over the state space. And you have this state S naught. I don't know, maybe this is your S naught. And then the next thing that we did is that we introduced this the distance. Well, the distance in a directed graph is like how many edges you have to take to travel from some node to another node in the graph. So that's our distance function. And then given the distance function, we introduced these sets S of age. And these sets were such that they collect all those states that are within a certain radius of the initial state, right? So for age equals 0, this is just S naught. That's just S. Capital S naught is just like the singleton that has the initial state in it. And then S1 would be, okay, you take the neighbors, right? So you can travel here one step. So these two guys, I don't know, call them A and B. So then this is S naught and A and B, and so on and so forth. Then we said that if we want to understand how well this procedure works, we better look at these errors, data H, which are the errors that arise if you raise this approximate Bellman operator to the power of H, light 0. Okay, no need for parentheses. Okay, apply it to 0, compare it to Q star. And the thing is that we don't want to compare these two functions everywhere. We only want to compare them where we can expect to see a small error. And if the power of h is higher, then we expect to see a small error only in a smaller vicinity of the initial state. So this suggested that maybe the error should be measured with respect to this max norm, where the maximum is constrained to those states which are at the distance of capital H minus h of the initial state. And then we derive this recursion, which was that basically subtract and add here t hat q star, and then use the triangle inequality, and then there are two terms. And one of the terms is going to, it was shown that it gives you a recursion, and the other term then just looks like as this deviation of t hat applied to q star and q star. And we inflated the errors here by saying that, well, let's measure this regardless of little index h. Let's just measure this across all the states that we could find within a distance of capital H from the initial state, starting from the initial state. And then we just want to control this error. And then if we can control this error, so maybe you call this epsilon prime. For some reason, I'm going to divide it by 1 minus gamma. That's going to be convenient. So let's assume, I mean, that's the definition of epsilon prime if you want, but no, I want a deterministic epsilon prime. So let's say somehow we prove that with high probability this is smaller than equal to epsilon prime over 1 minus gamma. Then you would have this recursion where you have that delta of h is smaller than equal to gamma times delta h minus 1 plus epsilon prime over 1 minus gamma. And okay, so what is that? So this is only true if h is at least 1. If h is 0, then delta naught is just 1 over 1 minus gamma, bounded by that, right? Because if h is equal to 0, then the result of applying the Bellman operator 0 times to 0, then you get a 0 compared to q star. So that's the norm of q star, and the norm of q star is at most 1 minus gamma. Okay. So we have delta naught smaller than 1 over 1 minus gamma. And then if you start the recursion, so this was true for h greater or equal to 1. So then delta 1 is smaller than gamma plus epsilon prime over 1 minus gamma. Okay. So delta 2 is smaller than, well, gamma times this guy, gamma times delta 1. So that's like gamma times gamma plus epsilon prime plus an epsilon prime from this second term, from the recursion over 1 minus gamma. And so that's like gamma squared plus epsilon prime times 1 plus gamma over 1 minus gamma. And you can see that if you continue this way, then there the capital of H, the quantity of interest, is going to be upper bounded by gamma to the power of H plus epsilon prime. And then here we have 1 plus gamma plus gamma to the power of h minus 1 divided by 1 minus gamma. This is upper bounded by 1 over 1 minus gamma. We are being generous here. And so this whole error is upper bounded by gamma to the power of h plus epsilon prime over 1 minus gamma times 1 over 1 minus gamma. The question is, how big is epsilon prime? Any questions? All right. So if we flip back, we see that epsilon prime, this was the inequality that was used. Well, there should be some high probability bound on this error. So why do I say high probability bound? Because t hat is random. So it may be that you are very unlucky with your sample here. So recall that these were generated from the next state distributions. Everything is independent of everything else. So independence, mutually independence holds between all of these random variables. Okay. But you can be very unlucky with the outcomes, and then very unlucky outcome. Of course, this is going to be very far. Oh, so why do we hope that this is small? Well, we hope that this is small because Q star is a fixed point of the Bellman optimality operator. And these two operators are like good friends, like siblings or whatnot. If you apply them to the same function Q and you compare what you get, you see that these guys do cancel, the gamma would come out. And what you should see as a difference, the difference between, the sample average for these neighbors that were generated at a state of interest and the sample mean. Sorry, not sample mean, the actual mean with respect to the distribution. So here, every S prime is generated from this distribution PAS. So we expect, by knowing many things about how randomness works, that these sample means are going to be close to their true mean, right? So here's the true mean, here's the sample mean. That should be close. Therefore, for every state action pair, they are close. So therefore, they're kind of done, right? Okay. So how do we finish this proof? Well, the first ingredient is going to be what's called Hovding's inequality. We have to also quantify how close these guys are. So it's not enough just to say that, well, as m goes to infinity, we are going to be fine. Maybe that's true. Maybe that's not true. Probably true. But we want finite computation. And the amount of computation that we do is going to depend on m. Right? So we want to know how big m should be to control the errors. And then we will calculate how much computation we are doing. Actually, we can provisionally say how much calculation we are doing, right? Because we already discussed that this is like a big recursion where you have like first branching because of the actions. So let's say you have two actions, and then you have branching because of the next state. You have m of those, and then this continues, and then this ends up in a tree of depth age, and the branching here every second floor, it's like MA. So roughly it's MA to the power of H plus 1, H minus 1. That's the order. Okay. So that's how big the tree is, and that's how much computation we're gonna do. That just follows from thinking about that this is a recursive call, right? Okay. Right. So we need to firm up like how big M should be to keep the errors under a tight control. We expect that if M is bigger, then this epsilon prime is going to be smaller. But by how much? So for this, we need a quantitative tool that allows us to compare sample means with true means. And this tool is what's called Hovding's inequality. And it's probably the most widely used or overused tool at the moment in, I don't know, lots of branches of machine learning. And this inequality is the following lemma or statement or theorem. If you have random variables which are, let's say, conveniently bounded between 0 and 1, and they are IID, independent, identically distributed, then and I goes from 1 to, I don't know, n, then for every confidence parameter zeta between 0 and 1, with probability at least 1 minus zeta, if you compare the sample mean of these random guys with their common mean, which is just the expected value of, let's say, the first guy, then the deviation can be upper bounded very conveniently with log 2 over zeta divided by 2n. We're going to take this lemma granted. The proof can be found many sources. I'm going to give you some sources. Bandit book is one of the examples, but there are lots of good stuff written about this. So just take it for granted. And we want to use this. Actually, we're going to need a strengthening of this lemma, which goes as follows. Very, very slight strengthening. And the proof of the strengthening goes exactly the same way. It is just like the strengthening is a bit more cumbersome to state, and so people are like, let's state the simplest form, but we all need the strengthening. So the lemma that we're gonna need is this. Everything is the same except, so if we have this xi, I goes from 1 to n, but we have a random element as well, like a random variable, a random vector, or whatnot, like some random element. And u and this x1, xn are defined over the same probability space, so they are jointly distributed. And let's say we happen to know that the distribution of the xi's given u is they're independent. So xi, xn are IID. They're not only independent, but they are identically distributed as well, even given u. So the meaning of this is that the probability that xi takes in value in ai, where I goes from 1 to n, given u, is the same as you take the product of probabilities of just calculating the probability that xi takes values in ai given ui, and you just multiply these. I just wrote out what this means, that these are independent given u. Okay. Then I call this C. Okay. C still holds. So nothing changes in the conclusion. So sometimes it's easier to reason about that some random variables are independent when conditioned on some other random stuff, given some other random element. And in this case, this version of the statement is useful. Okay. Oh, no. I was trying to save some time. No, this is not how it goes. You have to replace this. Ooh, clear page. This expectation is going to be conditioned on you. So what holds in this case is that for every zeta is probability at least 1 minus zeta, the sample mean deviates from the conditional expectation of x1 given u. So it's like stronger because we're comparing it with the conditional expectation by only as much as previously. Right, so the conclusion almost is the same, except that this expectation here needs to be replaced with the conditional expectation. Okay. All right. Anyhow, so we want to use these lemmas, any of them, whichever is convenient, to control this epsilon prime, or to control this deviation of t hat, q star, deviation between t hat q star and t q star on S age. And so this means that we need to control, if you just expand these operators, that at any given SA pair, everything cancels except that you find a gamma, and then recall that the maximum operator applied to Q star gives you V star. So you find that this is the same as V star evaluated at S, let me call it J prime SA. Okay, so that's one side, and the other side should be P AS V star. Oops, that's really compressed. That's V star. Okay, I should copy this on the other side, and you have to take the max over all actions, and you have to take the max over all states in S of H. Right. So again, it's T hat Q star minus TQ star SH. It's the max. It's double max of 1 over M. And then J goes from 1 to M. V star is J prime SA minus PS V star. And you guys have heard about union bonds, right?
Was a homework question.
Yeah, it was a homework question already, right?
Yes.
Right. So the way the union bonds, I imagine they work is that it is your probability space, omega, and then there are all these error events that correspond to different bad things that can happen. So there is one error event that is of this size, it's of size delta 1. There is another one that is of this size, it's of size delta 2. And then there is a third one, let's say that's a delta 3. And then if none of the error events happen, then something good happens. So for example, if none of these quantities over all possible state action pairs is big, then they're all small. Therefore, their maximum is small as well, right? Okay. So the bad event is when some deviation is large. If for every state action pair we have a bad event and we assign some probability to that bad event, let's call it delta. I guess maybe it should be zeta or something. Then we can sum up the probabilities of these bad events, and that bounds the probability of that any of the bad events happen. So that's the union bound, right? And if you had I don't know, SA times S times A possible state action pairs, and you assign an error probability of zeta for each of them. So for all SA, let's say probability, we know that from Hovding's inequality that, let's call this delta SA, all right? So I just call it delta SA. So Hovding's inequality tells us that for every delta SA, there exists a bad event such that outside of the bad event, data is small. How small it is? Well, V star is of the scale of 1 over 1 minus gamma, so we have to scale up the errors by the same factor. So they're just normalization for Hovding. And then here you have your sample mean after normalization. It's between like all of these guys are independent. They're identically distributed. The common distribution is just PS, right? They're obviously independent because they were independently generated. And if you apply some fixed function to them, then of course the result of that is also independent, right? So if you have independent things, you apply some fixed thing to it, then the results are still independent. It's like a basic result. And if you scale things, you find that Hovding's inequality can be applied, and you get that this is smaller than or equal to log 2 over zeta divided by m under the root times the scaling factor, like how big the values are. In general, that should be the range of the function that you are averaging over. So here, everything is between 0 and 1 over 1 minus gamma. That's our range. That's good. And so for every SA outside of epsilon SA, which is ESA, which is this bad event for some SA, and all of these are going to be just zeta then. Make it simple. So outside of this bad event, these inequalities hold. So outside of the union of these bad events, so here the order of quantifiers for every SA that exists a bad event, such that outside of that bad event, the deviation is small. Okay, so for every SA, there is a bad event. So now we take the union of the bad events. If we are outside of the union of the bad events, then none of the deviations are small. So all of them are small. So that means that the maximum of them is also going to be small. So if you want to argue with that maximum deviation is small, then union bound is your friend. So it's still this small because all of them are small. We're outside of any of these bad events. Like outside of this guy, delta SA is small. Out of this other guy, this other one, some other delta SA is small. So the complementary of all of this is what's left out here, which is this green region. There everything is nice. We never excluded these guys, okay? So maybe the only problem is that could be a very small region, right? In the probability space, because we carve away more and more and more. So the union bound looks gorgeous, but it can be very dangerous and can kill you as well. But it's always the first good attempt to try the union bound. So outside of this holds. So that means that you could take epsilon prime over 1 minus gamma this, and then you can claim that with probability, that is the probability of the complementary of this, at least that much, maybe more. Maybe like these bad events are actually smaller. They don't have zeta probabilities. But anyways, in those cases, the maximum deviation is small. All right, so this is okay, but what's the probability? So what's the probability with what's the probability mass assigned to the complementer of this set? So the probability of the complementer so that's just like 1 minus the probability of the union, right? And then that we get something smaller if we move this union outside and then take the sum. And Hovding's inequalities claim would be vacuous if we didn't say that here these events are such that their probabilities are individually smaller than zeta, right? So then this is smaller than 1 minus SA times zeta. If SA happens to be finite, let's say it's finite. Okay. All right. So if I want this to be, I don't know, some data failure, I want to say that with probability 1 minus data failure, the data failure is my choice. Then I just need to solve like how big should be zeta such that this failure probability is SA zeta. And so I get that zeta should be data failure, my target failure probability divided by SA, which is going to inflate my deviations here. So that goes in there. So that means that the epsilon prime that I'm going to get is going to be log 2SA divided by data failure divided by, okay, there's a 2 here, 2m. Right? Okay. This is okay to some degree. We're controlling the epsilon prime, and we can plug that in here. And eventually we want this to be smaller than equal to our delta. Okay. Because then we would be able to say what? We would be able to say that with probability 1 minus delta failure, this policy only selects delta optimizing actions. And then there is the infamous last exercise, which says that if that happens, then this policy is not too bad. If you can control the failure probability, you can push it down, like you make it small, and you can control this other data, then you're controlling the quality of your policy. So here we had like gamma to the power of h plus, and then epsilon prime. There was 1 over 1 minus gamma. We have a second one here. And then here we have the log of 2SA divided by the data failure probability over 2m. And the whole thing is divided by 1 minus gamma. And long story short, you want this to be small. How do we make this small? And at the same time, you want data failure, I guess. So if you have some target, then from the last exercise, the additional error, suboptimality, grows that comes from data failure is going to be 2 times data failure divided by 1 minus gamma squared. So let's say you have some target suboptimality data. You're going to split into 3 parts. So 1/3 goes here. That gives you the value of data failure. Okay? So you get the value of data failure. This is your target suboptimality. Okay. So you solve this for data failure. So it's basically data failure is like up to 1 minus gamma factors, it's data. So this data goes in there. Okay, so the next term, like we have to control this term and then this term. Well, controlling these terms can be done independently of each other. The only trouble here is that in order to control this term here, the m, we can choose m to be large. So we want this term to be of the size of, again, that over 3. And then this will be also that over 3. Like it's a very simplistic distribution of the errors into 3 equal parts because we have no better idea, and this is good enough, right? So from this, so solving for this, okay, you can disregard 1 minus gamma. It just gives you the effective horizon at the level of that over 3. So that's like a 1 over 1 minus gamma thing. So that gives you that H should be something like 1 over 1 minus gamma to some power, I don't know which, maybe 2 or something like that. Not even that. Yeah, it's 2. Yeah. And then some log factors. Fine. This other guy, this whole other guy should also be, the second term should be that over 3. So here the only control that you have is this m. So you can move this 1 minus gamma terms on the other side. You can square things. You can take the inverse. At the end of the day, what kind of spoils everything is that the number of states creeped into the log. So long story short, if you solve all of this, then the m is going to need to keep up with the log of the number of states. So m, you will find that to control this, m needs to grow at least logarithmically with the number of states. And if you don't like that, then this proof is not for you. Okay, so we set out that we want something, we want an algorithm that proves the case that you don't need computational resources that scale with the number of states if you do these things in a clever fashion. And here we are failing. So this is not good, right? So the only way we can control this is by making them big, but then it has to keep up with this log. So game over. So what do we do? Any ideas?
Shouldn't that be SH?
SH?
Yep.
How would, okay, one question, how would that happen? Why would that be SH?
Since our max is over SH.
SA pars. Oh, this SH, right. Okay, yeah, okay, yeah. Sorry. It's it would be easier if you could point. So you're pointing out that the max was not over all possible state action pairs. There we were just disregarding that the max was just over some states, not over all possible states. It was over the states which were close to S0. When you introduce this branching process and then you do like 8 steps. So we surely know that S of H doesn't have that many states. It can only have m times A to the power of, I don't know, h+1 states, right? So this is how many states I can access, generate with the branching process if I never generate duplicates, right? So that's good. So maybe just take the union bound over these. Okay. How will that work? Can we do that? How would we store, or how would we tell our union bound story? So the union bound story was here. So we had to name, like, what are the events, and then for each of those events you take, you know, like another event and so on and so forth. So the difficulty here is that this set is in an ugly fashion random. This is not like a fixed set, it's random, right? It depends on what next states are being generated in this process. Like, where was this? I don't know. Like, there is this process when you're generating the next states, and then it goes and goes and goes, and then you take as 8 steps, and it is random, right? Like the states that you can access, like we had this random graph. So in the random graph, the states, which are 8 steps, capital 8 steps or less to S naught, are the states which are accessible. And so since the edges were random, this whole thing is random. It's not so easy to take a union bound over this. So any ideas of what we should do?
This is probably wrong, but is there some way we can condition on SH?
Yeah, it's kind of, that's a tricky business. Conditioning kind of can kill easily any sort of independence, right? So the problem is that if you have a Markov chain, like let's say that this is your Markov chain, and it's really silly. So there is the state 1, can go to state 2. The probability of that is epsilon, which is really small. And then there is probability 1 minus epsilon. It goes to this other state. And then, I don't know, like here we are staying in put with probability 1 in both states. Then if you say that, okay, let's generate from state 1 a random next state. So that's like S or S prime. So that's very likely is going to be S3, right? And then you could say that, okay, but maybe the process continues. So I take some other random state. I don't know how I generated some other random state S random. They're jointly distributed. And then I want to maybe claim that the probability that S prime is equal to some S is the same condition on S as if I don't condition on S. Right? So it's like conditioning doesn't matter. Like that's the dream, that conditioning wouldn't matter. You have to be very careful because depending on how you pick this S, obviously this may or may not hold. And for example, if I pick S to be by definition S prime, that's very mean, right? So then, like, I don't know, like I call this, I don't know, 2. Like the probability of S prime is equal to, I don't know, let's make everything concrete. S prime is 2, given that S is 2, it should be the same, that probability is S prime is 2. So this is generated from the next state distribution at state 1. Then this guy is just epsilon, right? But if S is equal to S prime, and I observe that S is equal to 2, then I know that the probability of S prime equals to is 1, right? So then this is 1. So if I define my conditioning variable in an adversarial fashion, then I can mess up, right? Like independence is gone, the distributions of the states are messed up, so conditioning is kind of messy. So we have to be careful. But some sort of conditioning is going to be the way to go. And in particular, we could try the following. So we have this set of random states, S of H. And we could try to regenerate this by just thinking about that we have this tree view of the process. One more. Where is this tree? Here is the tree. And so all the states in SH are eventually generated by traversing this tree. Okay. And in traversing the tree, you can traverse the tree in many different ways. Let's say you choose depth first traverser. Okay. So this tree lists all the states in SH. And let's consider the depth first traverser of this tree. So maybe, you know, like, so here, this state could be the same as the initial state, right? Like a state can be listed multiple times, right? So that's the kind of the thing, right? But so the depth first traversal order is going to be like, oh, let's consider first this state, then this state. This may be the same as the initial state, or may not be the same, and go down. This is the this is, I don't know, the H's one. Then this is going to be the H plus ones, and so on. So first, you know, depth first traversal order. Okay, so this way you can create a list of fixed lengths, because the length is going to be how many nodes we have in the tree. So this n is going to be h m to the power of h minus 1, h plus 1 minus 1 divided by a minus 1, I guess. And so this is the depth first encounters of states in SH. So potentially n is much bigger than SH, but as sets they are equal. So of course, like, we are exhausting all the states in SH, and we're going to use this process view to argue that everything is still fine. And the way you do it is that we're going to prove that the union bound is going to be for all for all values that, let's say this index I can take between 1 and n. So we're going to prove the following lemma for all I in n with probability 1 minus zeta the deviation, okay, and for every action in A, the deviation that we get at this state SIA is smaller than or equal to whatever we get from Hovding. Right? And then we apply a union bound over all possible i's, and we'll be done because n is independent of the size of the state space. Right? So this is the trick that should save the day. And the way you go about this is that you introduce this index tau I. So you want to prove this. And I guess, okay, so the proof works by induction. Induction? I don't know. No, it's just like pick an I, pick an A, as said, define tau I as the smallest index k between 1 and I, such that sk is equal to si. Right? So clearly the tau I could be as large as I, but cannot be larger. It's going to be between 1 and I. Right? So this is the first encounter of state Si. Before this encounter, state Si didn't appear because the states were okay, and this this ordering that was created was such that okay, how do we want to argue? So we want to argue that there is this data SIA, and if you recall the data SIA, this was just this deviation of I don't know, S prime in the children of SIA, V star S prime minus, and then I have to plug in SI here, V star, right? So we want to argue that these guys, the individual terms in these guys are independent of each other and identically distributed, and their common mean is this. But of course, this is random. There is an SI, so we're gonna say, rather than this, we're gonna say that, well, this delta SIA is the same as the delta S tau I A. So if Si appeared earlier in the list, just take that state. And the children are the same, so they are equal. And we're going to argue about this guy. Okay. And so now imagine that here you have not Si, but here you have S tau I, and here you have also S tau I. Okay. So now I'm going to say that given S tau I, the children, so the children of S tau I and action A, those guys are independent of S tau I, given S tau I. So why? It's because S tau I, that's the first occurrence of this state in our list. And this is generated based on the children of S1 and then the children of S tau I minus 1. So in the tree process, no other children are participating. And by definition, these children, so for disjoint sets of states, the children of those states are independent of each other. So this independence holds. So now that independence holds, you can apply condition on S tau I, this modification of Hovding's inequality, and you get that delta Si is indeed of this size at most. Right. So once this is done, then you can apply a union bound. So the next step is union bound over I in N, put everything together, and I don't have time to calculate this, but it's almost there. So if you just look back what we had before, we just have to know that instead of this S, what we're going to have here is N. All right. And N is of the size of AM to the power of H plus 1 at most. Okay. So the H comes out of the log, and then the M has to keep up with basically H log AM. And then you may vary about that M is on both sides, but you can actually solve how big M should be so that whole thing is controlled. There will be an additional log A term. So roughly M has to be H log A up to log term. So if you put everything together, then we see that the total work, so the cost is bounded by MA to the power of H, where H was roughly H gamma, and then 1 minus gamma, I think, some power square delta. And M has to be H log A. And with this cost, the algorithm, the local planning algorithm, gives policy such that the policy is at most delta suboptimal. And this was first described by Kearns, Mansour, and Singh in the 2010 paper. And this was first described by Kearns, Mansour, and Singh in the 2010 paper. And this was first described by Kearns, Mansour, and Singh in the 2010 paper. And this was first described by Kearns, Mansour, and Singh in the 2010 paper. And this was first described by Kearns, Mansour, and Singh in the 2010 paper. And this was first described by Kearns, Mansour, and Singh in the 2010 paper. And this was first described by Kearns, Mansour, and Singh in the 2010 paper. And this was first described by Kearns, Mansour, and Singh in the 2010 paper. And this was first described by Kearns, Mansour, and Singh in the 2010 paper. And this was first described by Kearns, Mansour, and Singh in the 2010 paper. And this was first described by Kearns, Mansour, and Singh in the 2010 paper. And this was first described by Kearns, Mansour, and Singh in the 2010 10s. So roughly 10 years old, something like that. And they, the way they describe it is a little bit different. So they don't emphasize this T of the approximation, the random approximation to the Bellman operator. They rather take this process U and what we discussed at the end with Roshan, that when you're doing this recursion, you can get fresh samples in every call. And that uses a little bit more queries, but the same result applies, kind of the same proof. I like this U because it emphasizes the importance of all these contractions and that you are approximating essentially the Bellman operator. And if you approximate the Bellman operator well, then you did everything that you had to do. And there is this also this very close connection to value iteration. This can be seen as just like a fancier randomized version of value iteration that avoids superfluous calculations. And it should be quite intuitive. And there is a big afterlife of this work. So lots of people worked on improving these algorithms further. Remy Munoz has written a short book that describes various ways you can save. I've been working on this a little bit as well. And in the worst case, we already mentioned that this exponential computation in the planning horizon cannot be avoided because you can plant a needle at one of the leaves, you can have a deterministic system, and then you have depths of age, then you have too many leaves, and all of them have to be checked out to be able to tell which way to go. Even at the root, you only have 8 choices altogether. This is the hardest of the problem. But there could be much nicer, smoother problems. And when that happens, then you can have smart algorithms that are going to induce big cuts. And they are directing exploration in fancy ways. Optimism comes in. We will talk a lot about optimism in the future. I guess already in the next class, we're going to talk about this. And we will see that optimism really does help, even though I haven't defined what optimism is going to mean. It kind of just means that, well, in this local view, there is the unknown parts of the MP you don't know yet about, and you can just treat them as if they were the best possible of all words. And that gives you action values, and you just choose the action always, which seems to be the best. And even though you're not doing any online learning, already in planning, optimism is going to give you nice savings. All right. Let's stop here. You guys have any questions?
So there's a question that why can't we directly replace S by the size of SH? Why did we have to prove that
So the
independence
size
thing?
of, okay, yeah. Good point. So SH has a random size. So we don't know how many elements are there because there could be duplicates of this list. So maybe there will be fewer elements. So then again, like you don't know how many elements the union bound needs to be taken over. So it's better to over-generate. If you want to take the union bound, you have to take the union bound over a fixed number of things. Like you can just say that like, a random number of things.
But in the worst case, isn't it just all unique, like states? So you just take it over am to the power of h plus 1, like we did there?
I mean, if you follow this proof, then yes, you can do that. But to be able to formally reason about it, I don't know of any other ways. Yeah. So I encourage that you try, because it's very educational to see how things don't work for most of these ideas. So if you try to take a union bound, like try to write it carefully. Like, what does it mean that I'm taking this union bound? Okay, why does it fail? So for example, if you can take union bound over infinitely many elements too. Like that's not a problem. If the sum of these failure probabilities sums to some small value, that's fine. Like we a lot of times do that. So it's not the coordinate is the question, but like how do you control the errors of all of these things? If you have, like it's just tricky business sometimes. In this case, it's kind of tricky.
But don't we know the error of each one of them is bounded by the Hovding bound?
Which one of them? Like if you try to write down which one are you talking about? Like
of any state h?
So here, like we do have this lemma, all right? So I can prove this. And this concerns every element of S of H. Mm-hmm. You might think that, okay, I'm just going to list these guys in an arbitrary order, like call it S hat 1 and S hat, and then a random number of them, capital N, right? Because we don't know how many there are in this list. And then try to apply this thing or something like this. Like, how do you do this? Like for every I between 1 and capital N, that's already kind of fishy. N is random. Okay, then like where is I going? Okay, so maybe we still want to replace this N, but then what is the event that we're going to name? Like what does I correspond to now? We can try others. I tried many things actually, because I wanted to simplify this even further, like have something really, I don't know, like just avoid this reasoning with the stopping times. But no, I think that I can't do it. It kind of reminds me of like what Du once wrote. Okay, this sounds like a little bit sad-boring, but like he's like one of my heroes. He's a very good guy. Writes books, and like in a preamble of one of his books, he writes that I try to write all of these things without measure theoretic probability, and then I kept rewriting it because I kept discovering errors. And after 5 years, I have to give up, or 10 years, I don't remember. And so he didn't give it easily, but eventually he was converted. And sometimes these reasonings are just like so much cleaner and easier. It's just like, at first it feels a bit free, but yeah.
Thanks.
Yeah, you're welcome. These are very good questions. It's worth to struggle on these. Okay, anything else?
So this is maybe a related question, sort of. So this proof, like you sort of said, like it was a proof of this algorithm, right? But am I wrong in thinking that what the algorithm is actually doing is that it is constructing sort of an empirical MDP, using samples from the real MDP, and then it is just doing value iteration on that empirical MDP.
That's my view.
So in principle, you could construct this proof in a way that says that if I construct an empirical MDP using this many samples from the real MDP, then the optimal policy in that empirical MDP is this close.
Yeah, just do that without relying on a number of states, like how many states there are in the MDP. Of course, you can do this at the log price for the current of the states, which is already kind of neat, right? But but if you want to completely avoid the bound to depend on the number of states in the state space, and there is no other way. Actually, you have to. It's like the budget for this algorithm is infinite if you run it for infinitely long, as opposed to something that you might think that, like, for every state action pair, once I draw some next state samples and I use this empirical approximation to the MDP, I just use this forever. This is a finite budget, the other has an infinite budget.
Okay. And the reason you can't sort of prune that way of thinking is because there is always some tiny probability that you could, like, even if you're doing a finite tree, there's always some small probability that a tree can include potentially any state in the MDP. So you are sort of forced to consider every state.
Yeah.
Okay. Yeah. Thanks.
Hi, just to rejoin. I don't know if this question is asked or not. Just you provide a second proof that we only depend on N, not the whole state space. Is that because we have the condition? When we condition on the possible states in the tree, and we have that, we can do that condition because we do. You can see we do depth first search. We only record the first element, so we can do that condition.
That's right. That's right. Because if you think about how this state is generated, this S to Y state, it is generated based on what are the children of the states that came before it. Okay, they determine what the identity of this state. But given the identity of this state, the children of this state in this process, because this is the first encounter of this state, are independent of, like, how we came to this state. Right?
Okay, thanks. Yeah.
Okay.
Also, briefly, you mentioned earlier that like, if you were slightly smarter about it, like you were talking about if you have the table representation of the probabilities, then you can't avoid linear dependence on number of states. And then you said something about like, if you're smarter and you sum up the probabilities, then you can get log dependence on the number of states.
I mean, if someone else sums up the probabilities, so you don't have to do that.
Right,
but someone
like,
hands you a representation where the probabilities are summed up, then you can do kind of like the averages can be calculated much faster, right? So because you can kind of search them. There is monotonicity. If you think about, like, what happens for the deterministic system, which was the hard case, there is a single jump there. And if you want to find a single jump, then that's like a binary search. So then you can generalize this.
Okay. And I guess you can also sample similarly.
Oh, and then you can also efficiently sample given such a representation. That's right.
Okay.
Yeah. Yeah, even sampling from probability tables, the complexity of that is going to depend on how the tables are represented to you, right? Okay.